in the last class, we were looking into the benefits of biasing a transistor using a constant current source instead of putting a voltage bias between the gate and the source, right? And this is what we were discussing as to how to go about doing it. And in case of an NMOS transistor, for example, if we the whole purpose was to say that we would like to use a constant current source because we don't want the current to change. So now we saw that if we just connect it like this, it's not going to work. Why it's not going to work? Because the current through the drain and the source of a transistor is essentially the effect. It's not the cause, right? Cause is the VGS, effect is IDS. So you cannot simply put IDS and hope that VGS is going to develop magically. So which means that we had to put our VGS separately. And the issue that we found with this was now there are essentially two independent sources, or rather two independent variables, right, in the circuit. So one is this voltage source, which is asking the transistor to, so let's say this is VGSQ. It is asking the transistor to bias itself at a current of IDSQ. And this is only going to work if magically somehow IDSQ is exactly equal to I0. And it did not necessarily be the case because of changes in temperature, because of changes in ambient condition, because there might be some, some inaccuracy in calculations of your current, right, to the nth decimal place. It need not be the same. So if it's not the same, then there's a problem, because now this guy is asking the transistor to get biased at IDSQ, but this guy is saying that I cannot provide IDSQ. Right, so you have a conflict, and the conflict is the conflict arises because you have you are trying to use two independent sources to bias a single transistor. Okay, and there is only one cause and effect scenario here. There cannot be two causes and one effect, right? So that's the problem. So then we said that okay, if this is not possible. What is the other thing that is possible? Other thing that is possible is we did a hypothetical experiment. Essentially, we're trying to visualize. Let's say we have to do this in the lab, right? So what are we going to do? So the stuff that we were thinking about was, let's say we are in the lab and we want to figure out whether we want to bias this transistor with I0. So we know that VGS is the cause, which means we'll add a variable voltage source at the VGS, right? We add a variable voltage source at VGS. And the whole purpose is to observe the current. And observe the current in such a way that the transistor is in saturation, right? So now, if let's assume the transistor is not in saturation, right? For example, I just plugged in a value of I plugged in, let's say 3 volt here, and I observed this voltage. And sometimes it becomes easier to visualize the flow of current if you assume there is a capacitor associated with it, small capacitor, right? So let's say a parasitic capacitance associated with it. So when we are talking about when something goes up and something goes down in terms of voltage, we are essentially talking about some effect of time. And it becomes difficult to visualize if the effect of time in a circuit if there is no capacitance. So just for the sake of visualization, I'm putting the capacitor CP. So now let's assume for the time being that under the condition that we have shown, your IDSQ is greater than I0. So if IDSQ is greater than I0, this voltage, let's say V0, the drain voltage V0, what's going to happen to V0? It's going to decrease, right? Because you are essentially, the amount of current that is getting pushed into this node is lesser than the current that you are pulling out. And that excess current will come from this capacitance CP, and it will pull the voltage down. So this means that your V0, or let me call it VD, the drain voltage, is then VD decreases. And if it's other way around, if IDSQ is less than I0, then VD increases. Okay, so now we have a handle, right? Because it is easy to observe voltage. What we postulate is just by observing the direction in which VD is moving, I can figure out if the transistor is biased properly or not. Right? If VD is going up, I know that the amount of current that I am pulling out through the transistor is insufficient. And if VD is going down, I know that the amount of current that I'm pulling out of the transistor is more than I know. So that node voltage has the requisite information. Do you agree with that? Okay. So now let's flip the argument other side on its side. Yes.
So, could you please explain again the reason behind the capacitor?
Okay, so it is mostly for visualization purposes, right? So anyway, there will be a capacitance associated with any node in a circuit, however small it might be. So for this argument, for today's lecture, I have put it the capacitance just to make you understand. If I say that the voltage is going down and going up, which means some current is flowing into or out of that voltage effectively. It's difficult to visualize if it's an open circuit where the current is going in and out. So that's why I put a capacitor to give you a sense of time with regards to if the voltage is going up, the current has to be flowing somewhere, right? Where it is flowing into the capacitor. Okay. Okay. So now if we flip the argument and try to look at it from other side, that is, we have connected the circuit in certain way, and the only way to observe whether the transistor is biased properly or not is to observe this voltage VD. Okay, so if I observe this voltage VD, all I need to then figure out a way of coming up with a framework to understand simply by observing the direction in which the VD is moving, is the transistor biased properly or not. Okay, and if it is not biased properly, then I have to take some action with regards to the gate to source voltage, right? Because that's the only handle. The gate to source voltage is the only handle to affect the current of the transistor. Okay, so now what will be the algorithm? The algorithm will be if VD increases, right? So if let's say start with the other way around. If VD decreases, then what is the conclusion? VD decreases means the transistor is trying to pull out more current or less current? More current, right? The conclusion is IDSQ is greater than I0. So what is the action that I need to take? Right, so action required is decrease VGS, in this case VG because source is grounded, right? Decrease VG. So action required is decrease VG. And if it's the other way around, if VD increases, then the conclusion is IDSQ is less than I0, then action required is increase VG. Right? So if this is what we are supposed to do, right? So again, the conclusion is if the algorithm is if this increases, I need to increase this. If drain voltage decreases, I need to decrease the gate voltage, right? So what is the easiest way to do that? Simply connect the gate and the drain. Okay, so if I simply connect the gate and the drain, firstly, this is what a logical thought process has led to, but it's not necessary that always the intuitive logical thought process will give you the exact answer, right? So, but we have to then go ahead and figure out whether this transistor is indeed biased in saturation, right? Using analysis. So what do you think? Is your transistor in saturation? What is the condition of saturation? VD should be greater than VG minus threshold voltage. Do you think this condition is getting met? it is of course getting met. In this case, VD is exactly equal to threshold voltage. Sorry, exactly equal to the gate voltage, right? So hence the transistor is in saturation, right? So now, so now the interesting part about this is, so let me write out the current equations. So in this case, the VGS, this VGS is getting set up by the current source, because you have some way of feeding back the information from the output to the input. So there is a feedback effect, right? Do you see that? There is a feedback effect because you're observing the output and taking an action at the input. Correct. So there is a feedback. And what is the independent source in this network? I0. The current is the independent source. And what is the dependent variable? VGS is the dependent variable, right? So now by putting a feedback, we have essentially reversed the dependent and independent equations, right? We have flipped the equation on its head. So the more prudent way to write this equation now becomes VGS is threshold voltage plus right? Essentially algebra. But the way you write the algebra can give you an idea as to which is the dependent source and which is the independent source. In this case, I0 is the independent source, and you are developing the VGS. You are asking the transistor to develop its own VGS. I'm pushing in the current I0, and I'm asking the transistor to set up that value of VGS, that magical value of VGS, for which always a current of I0 is going to flow. Right? I'm not saying anything new, but I'm trying to put in a new perspective. Okay, so why is that statement important? The statement is important because if I compare this with a common source amplifier biasing, let's say this is what I'm comparing with. So let's say the threshold voltage in this case, let's say this is A, this is B. In case of both, either A and B, the threshold voltage changed. Let's say the threshold voltage was 1 volt, it's changed to 1.1 volt. So what's going to happen in the circuit in the B? The threshold voltage increased in both cases. Let's say we are talking about the bottom circuit. What's going to happen to IDS? The IDS is going to decrease. Right? I mean, nothing profound in that. The current equation is directly telling you that. But what is going to happen in the circuit in the top? So the threshold, since it's biased with a constant current source, there's no way the current is going to increase. Then something has to change. What's going to change? VGS rate is going to change. How much the VGS is going to change? By exactly the same amount by which the threshold voltage changed. Right? So if threshold voltage goes by VTH plus delta VTH, the VGS will also increase by the same amount. Right? So essentially you are, whatever you would have done in the lab, right? You would have observed the output voltage and tweaked the threshold, tweaked the VGS. That's what this circuit is doing automatically. Okay, so you needed some magic voltage. Let's say you put in any arbitrary current I0. Maybe the I0 is, I don't know, some function of E or pi, irrational number and all, right? You cannot ever fix that voltage. Whatever you try to do, there will be some error, right? So if there is an error, you'll never be able to bias. Even if you take infinite time with a potentiometer and to fix the VGS by putting whatever resistor divider that you want. But this circuit here will develop that magic voltage VGS that is required in order to give you that exact current. You don't have to do any calculation. The circuit does the calculation itself. Right? Make sense? Okay. Okay, fine. So this is all good. But then the question naturally comes is, This is only setting up the VGS. How do I apply an input, take an output? Ultimately, we want an amplifier, right? So let's go back to our good old common source amplifier. I want to bias it with a constant current source, which means at quiescent, I want this current to be equal to I naught, right? So it's important to first address what we want, right? So we want IDS to be exactly equal to I naught, where I naught is equal to constant. So there is some current source somewhere available, which is giving you I naught. I want to ensure this current through this transistor is whatever it is exactly equal to I naught. Okay. So if this were to happen, so this is I naught equal to constant with respect to any change in temperature or any change in ambient condition, which means I need a constant current source by definition. So if I need a constant current source, now we know that using this is not a good idea, right? So any change in threshold voltage, your current is going to change. So it's not a constant current source bias. So if that's not the case, what is the other thing to do? The other thing to do will be to recognize the fact that I want this VGS to be equal to, somehow I need to figure out a circuit which gives me that magical value of VGS, which will ensure that the current through the transistor is always equal to I naught, regardless of whatever threshold voltage or mobility or whatever there might be, right? So this VGS has to be equal to threshold voltage plus 2 I naught by mu and C ox W by L, right? Which means that this VGS has to be a dependent variable. The way I have written, it means that VGS has to be the dependent variable. So how do I develop that VGS? Let's say you can use multiple transistors. So how can you develop that VGS? Is the question clear? Okay, let me ask you this way. Let's say I do the calculation of the VGS that is required. I put a voltage source here. So is this going to work? No, right? So which means I need a variable voltage source, right? Essentially, I want a dependent voltage source, kind of, right? We want a variable dependent voltage source. And how do I get that voltage source? How do I get that voltage, rather? I shouldn't say voltage source. How do I get that voltage, which is dependent on threshold voltage? Because if it's not dependent on threshold voltage, if threshold voltage changes, the overdrive is going to change. Because transistor current depends on the overdrive. It's VGS minus VTH that I want to remain constant, right? Not VGS. I want the overdrive voltage to remain constant if I want the current to be constant. So how do I get that voltage? How do I get that overdrive? Yeah, but connecting both of them means? Yeah, right. So the issue, I'll tell you what's the issue. The issue is if I do this, how do I then connect the input? Because gate and drain are shorted now. Because when I am applying an incremental input, I want the gate and the drain to be isolated, isn't it? Because the input has to go to the gate and the output will come from drain. But by the way I have generated the bias, I cannot do that. Pardon? That is actually one of the ways people do, but not for this course. So there is an easier solution, right? So can you put 2 and 2 together in the sense that whatever we did, it not be limited to a single transistor. I can use a different transistor to generate the bias and apply it here. Pardon? I think I heard something. So again, don't limit yourself to single transistor. Let's say you have infinite number of transistors available. So what are you going to do? You have a current source, you have infinite number of transistors. What are you going to do? Huh? Yeah, I think you are right. Yeah, exactly, right. Put another MOSFET, and how do I connect that MOSFET? Yeah, right. So we already know how to generate this magical VGS. This voltage is this VGS, isn't it? Yeah. So if I have this, then I simply connect these two.
Then what is the need of this one?
I'll come to that. This wire is not required. Yeah. Yes. We are using the I0, but you'll shortly see why this is more effective than the other one. But do you agree that whether if I do this, this will get connected with a constant current bias? Yes or no? So let's what I'm essentially saying is, let's say now the threshold voltage has changed. Okay. And further, let's assume we have to make an important assumption here. Let's say M1 and M2 are identical. That is, their threshold voltage are same. And if one changes, threshold voltage of one changes, threshold voltage of the other also changes. And that is more or less true when you are putting everything in an integrated circuit, because it's such a small amount of area and you are making them using a batch. So whatever is happening to one transistor, exactly the same thing is happening to the neighboring transistor. So that's a given. That's one of the good things about integrated circuits. So if that is the case, now let's assume that the threshold voltage has changed by 100 millivolt. What do you think is going to happen to this VGS? It will change by the same amount. So what do you think will happen to this current? Will it? It will, because the overdrive is remaining constant, right? What is the overdrive? Overdrive is VGS minus threshold voltage. So this is equal to 2I0 by mu n Cox W over L. So I0 is not changing, right? W by L is not changing, mu n Cox is not changing, which means your current will not change as well, right? Make sense? So even if the threshold voltage changes, if you bias your circuit like this, it's not going to change the current, right? Okay, so if you agree with this, then we have to, yes. Okay, so in general, it doesn't have, but there are some effects because there's a common reason why threshold voltage changes is temperature change. If there is a temperature change, it's going to have some effect on it, right? We'll talk about that later, right? Let's concentrate on threshold voltage change, right? So okay, I mean, we can also address it right away. So let's say the threshold voltage changed and it had an effect on mu, right? Let's say both of them change. Threshold voltage also change, mu also change. So do you think the current in the left branch and the right branch will be different?
Sir, but we are doing it to make identical incremental network. No? If mu changes, then it will not be identical.
Yeah, it will not be identical. We'll do that analysis of how much it will change shortly. But with regards to the currents in the left network and the right network, we think the quiescent time will be different even if threshold voltage and mu changes. No, right? Because ultimately, what's going to happen? So ultimately, this current. Can you comment on, regardless of whatever happens, if M1 and M2 is identical, this current and this current, right? So let's say this is I1 and let's say this is I2. Can you comment on I1, relationship between I1 and I2? I2 will always be equal to I1 because whatever is happening to the circuit on the left, the same thing is happening to the circuit on the right with regards to quiescent currents. Both of their VGS is same because that's how they are physically connected. If the VGS is same, and as long as we ensure the guy on the right, the M2 is in saturation, then the currents has to be identical. Correct? Does that answer your question? Okay. So now let's see what, I mean, this is only the biasing part, right? The full picture is not yet over, right? So we have to figure out a way of connecting an input and taking an output. So at least by doing this, what we have done is we have isolated the gate and the drain of M2. Yes. No, purpose of closed setup was not to produce an INR. What I am saying is we can use a constant current source, but we have to use a constant current source to bias the transistor. Just like we have a constant voltage source, actually we have a constant current source. So if I have a constant current source, how do I put it in the circuit to ensure that the transistor gets biased? The issue was the current in the transistor, as we know it, is the dependent variable. It's the effect, it's not the cause. So what I am essentially, if I just stick in a current source to the drain, what I'm saying is that this is the cause, give me the effect. Right? So how am I generating the effect? By putting the feedback between the drain and the source, drain and the gate. Right? So now once we have a trick, right? Yes.
If I2 is equal to I1, it also depends on the resistance value.
Okay, how does it depend on resistance value?
To make it in the saturation.
Yes.
Because it will be VDD minus ID.
100%. So his point is, I simply cannot connect it like this and assume that the transistor, both the current will be equal, because we have to ensure that M1 and M2 are in saturation. By M1 is already in saturation because drain and gate voltage are same. We have to ensure that M2 is in saturation. So we cannot use an arbitrary value of the resistor. But that is a designer's choice, right? So I can at least ensure that the value of R is not such that the transistor goes out of saturation. But that's a very good point. Okay, so let's assume the transistor is in saturation, right? Just like in a common source amplifier, we assume many things and then figured out way of finding out the component values. So let's assume the transistor is in saturation. So again, to a quick recap. So using only this configuration, it was becoming difficult to add a voltage source and take an output, right? Because gate and drain were physically connected. I don't want the gate and drain to be physically connected. The gate has to be the place where gate to source is the place where I'm planning to apply an input, and I'm planning to get the output at the drain, right? So if I physically connect the gate on the drain, that's not going to serve the purpose. But in this case, at least now I have isolated the gate and the drain, at least for M2, right? So which means that I have opened up a avenue of applying this is VI, this is RS. I have opened up an avenue of applying an input between the gate and the source of M2, right? So now can you tell me a way of applying the incremental input between the gate and the source of M2? The source is grounded, so essentially the incremental input has to be added to the gate. So how do I go about doing it? Between? You mean?
No, connect the register and voltage source like this. Connect the register.
Okay.
And then a voltage source.
You mean some resistor?
No, between the these of both. If we connect the register.
Okay, let me mark the points, right? So let's say this is terminal 1, this is terminal 2. So
connect 1, 2.
Okay.
And this where B and G are joined. Connect a resistor between both. Like replace the wire with a resistor.
You mean here?
No, not here.
I don't understand. So this one? Maybe can you come up here and tell me? Okay, tell me what. That GT. Yeah. They are anyway connected, right?
Connected resistors.
Connected to a resistor.
VI. Like VI.
Okay, this?
No.
Is this what you want or what? No, tell me, I mean.
Yes, I connect 2 and 1.
Fine. Okay. So let's see whether this is going to work. So let me put this value as RG, right? Or name it RG. Okay, fine. So moment you connect something, first thing you have to check is the quiescent getting disturbed or not. So do you think the quiescent is going to get disturbed? Yes, right? When I'm talking about quiescent, Vi is essentially 0. Right? So there will be a current. Right? So there will be a current which will flow in this route. Correct? So if this, so what was this voltage earlier? This voltage was that value of VGS for which I needed a current of I0. But now there will be a, so this I0 will not only flow through M1, part of the I0 will flow through RG and RS into the ground, right? So firstly, that voltage will not be equal. That VGS is not the magic VGS for I0. For some other current, now it becomes that VGS. And more importantly, the voltage at 2 will be lower than the voltage of that VGS, right? So the current through M2 will not be equal to the current through M1. Okay, so this is not going to work right away. But then we have a solution, right? In order to isolate the voltages. Again, so what is the main reason that when I'm connecting these two, current is flowing? This main reason it's flowing is because the quiescent value of this voltage and the quiescent value of this voltage, when they are not connected together, are not identical. If they were identical, then no current would have flowed, right? So what is the easiest way to make them identical? Put a battery of value which is exactly equal to the VGSQ. Then if I connect them together, it's okay, right? So but putting a battery is infeasible. So what we do? Put a capacitor. Okay, so if I put a capacitor, at least now we see that, quiescent wise, there is absolutely no change, right? So quiescent operation, you don't even have to bother to analyze. Let's analyze what's going to happen to the incremental network. Yes. Okay, he said RG, that's why I put RG. So I'll remove RG. So even with, now even if RG is not there, if I connect it, even then this is not going to work because part of I0 will flow through this, right? So the current through M1 will be less than I0, right? So that VGS, the magical value of VGS will be lesser than, it should be lesser than, it will be lesser than whatever it is required for a current of I0, right? So it's not going to work. So the best thing to do is not connect it like that and connect it through a capacitor. Okay, fine. So now let's find, so moment we have a capacitor, we have to figure out what is the value of the capacitor that is necessary to ensure that it behaves like a short circuit for the frequency of interest. Okay, so now we know, right? We don't even have to do much calculation. It's all related to time constants, right? So what is the time constant associated with the capacitor? It's Rs times C or it's something else. So again, so let's draw the incremental network for this case when we are trying to figure out the resistance across the capacitor, right? So let's do the incremental network. So start from the left. So this is open. What do I replace M1 with? So this is the gate, this is the source. So this is GM VGS, right? Drain and the source are connected. Here I have GM VGS. Then there is a resistor incremental to ground. There is this capacitor. And there is a resistor RS to ground, right? I'm trying to figure out time constant, so I don't need Vi. Okay, so let me draw it in a better way. This is quite clunky. Okay, so when I'm trying to figure out the equivalent impedance looking across the capacitor, I don't need the capacitor. Instead of that, I can simply put a voltage source and try to figure out what is the equivalent impedance. Essentially, what I'm looking for is if this is the terminal, right? If this is a black box and I'm looking in through this, what is the equivalent impedance? Right? So an easier way to do is, I mean, this side looking down, right? Looking down, it's RS because the RS to ground. We don't have to bother. Just that I have to figure out looking left. If I know what is looking left, then that plus RS will be the equivalent impedance. Right? So essentially the circuit then, I mean, the stuff that I have to figure out becomes what is the impedance of this circuit. When I'm looking from this side. Okay, let's think about it, whether it's infinite or not. Yeah. So what do? I apply a test voltage. If I apply a test voltage, source is anyway grounded. So this becomes Gm times V test. So the current that I'm drawing is Gm times V test, which is equal to I test. So equivalent impedance RTH, right? So the R in this case becomes 1 over Gm. Okay. So this is also an useful configuration to remember. So this configuration that we see, so assuming this is biased, when the gate and drain are connected, right? So this is often called a diode-connected configuration. In a diode-connected configuration, the impedance looking in is 1 over Gm. So this is a very handy thing to remember. We can use it multiple times as is instead of writing out the sketching the full network. Okay, so now if this is the case, let me go back to this original circuit. So from the capacitor's perspective, looking this side is 1 over Gm. Looking this side is Rs. So what will be the time constant? 1 over Gm plus Rs times the C. So tau becomes 1 over Gm plus Rs times the C. And this has to be what? With regards to omega naught? For the capacitor to behave like a short circuit at omega naught? Yeah, it should be much greater than 1 over omega naught, right? As long as you can choose these values, you are good. Okay, so let me redraw. Okay, so as long as I can ensure that this condition is met, the capacitor will behave like a short circuit at frequency of omega naught. But the issue is the value of Rs is not in your control, right? It comes with the source. Okay. You might argue that the value of Gm is in your control. To some extent it is, but if you change this Gm is also going to change because M1 and M2 are identical, right? So you would like to have a sort of independent control of either of them. Okay. So one might argue that Gm is a function of W over L. I need not have the same W over L in M1 and M2, right? So you can think about it. That is a possibility. Yes.
I think the current in incremental network, current source will be open circuit, and there will be no chance to flow for current source, so it will be VI. No?
Okay, so why? Okay, so his point is, looks like the in the incremental network, this current source will be open. So, so looking on the left-hand side, looking this side, is open circuit. Is that? But is that an open circuit in the incremental network? It's not, right? It's 1 over GM. It's actually quite low, I would say, right? So because ultimately what's going to happen, this moment this voltage jumps, the VGS changes, right? If the VGS changes, it's going to, the transistor is seeking out more current. Where from will the current come? The current will come through this. It need not necessarily come from the current source because there is another path. Okay. Okay. Okay, fine. So now I don't want to tamper the GM. RS is not in my control. So one way to argue is that put a very large value of capacitor and this condition is going to be met. Now, the problem with putting very large value of capacitor is you can put very large values of capacitor on a breadboard because they all look the same, similar size. But in an IC, in an integrated circuit, the capacitance, in general, what is the capacitance is a function of the area and the thickness between the plates. Now, thickness between the plates is technology dependent. You cannot change it, right? It basically, when you are making an integrated circuit, it will tell you that you have multiple layers of metal and they are only separated by fixed amount of thickness. You cannot change it. You can only change the area. That is the designer's control. So if you want very large value of capacitance, essentially you end up using a very large value of, I mean, a lot of area on an IC, and it's super expensive. So whenever when you are designing, one of the major goals is to ensure that you don't take up a lot of real estate on an integrated circuit. So even though this probably tells us that having a large value of capacitance is a solution, which indeed it is a solution, but it will be a very costly solution, right? So we want to save money. So if that is the scenario, how does that economics affect engineering? So what should we do to ensure that we get whatever we want, but still not get affected by very large value of capacitances, or rather I have to reduce the value of the capacitance. Where I put a resistance in series with RS, right? So you can put a resistance in series with RS. Okay, so if I put a resistance in series with RS, so let's say I call it, I don't know, maybe R3. Okay, so what's going to happen? So let's look at the incremental network, right? Again, let's look at the incremental network and see whether this is going to help us, because so if I draw the incremental network, I know that while I'm trying to figure out what will be this voltage, what will be this VGS, I don't need M2 because M2 is not affecting VGS. So I just disregard M2. So what am I saying? The capacitor is shorted. I have R3. Yes. Okay, so the problem is, so I want, so let me maybe rephrase, right? So what is the goal? The goal is the capacitor should act like a short circuit, right? And what is the purpose? The purpose is I want the entire VI, almost the entire VI to appear between the gate and the source of M2, right? That's what common source amplifier should look like. Yes.
It should be better than the point where earlier RC was.
Yeah, I will come to that. So there are two aspects to it. One is the capacitor has to behave like a short circuit. Another aspect is VI should almost the entire VI should come here. Right? So the capacitor behaving like a short circuit is kind of satisfies the top end, right? So now on the top you see it's like 1 over GM plus RS times C. RS you cannot change, is given by the source. 1 over Gm, I wouldn't like to touch to the first order, right? Because if I change the M1 Gm, M2 Gm is going to change. They're identical. Which means that the only handle that I have is the value of the capacitance. They have to increase the capacitance to humongous amount depending upon what the time constant I want, and that is costly, right? That will cost us, the cost of your cell phone will go up for event. So if that is the case, then obviously you cannot do that. Then what is the other solution? Or what is the possible solution? His argument was, I mean, all I am trying to do is increase this time constant and don't want to play with C, I can simply add another R, right? So where should I add? You can add down anywhere in this loop, which is setting the time constant. So, so the idea was to put an R3 here. So essentially your new time constant will be 1 over Gm plus Rs plus R3 times C. And this R3 is a designer controllable variable. So I can keep on increasing. But the issue is, you see, in the incremental sense, what is this loop? This loop is nothing but 1 over Gm. I'm now simply writing 1 over Gm because I know that impedance here is 1 over Gm. Then capacitor is a short circuit. Then you have R3. Then you have RS. Then you have Vi. And here, this is what the VGS is. Right? So what will be the VGS? Your VGS will essentially become 1 over Gm by 1 over Gm plus RS plus R3 times Vi. Right? And this can be a potentially very small value, right? If you make R3 to be really large. Right? So putting R3 in the loop achieves the time constant objective, but it doesn't achieve the objective of Vi appearing as is. Then the solution that he pointed out was, instead of putting R3 here, why don't I put R3 here? Right? So this becomes 1 over Gm R3 plus 1 over Gm. So under the limiting case, is R3 is much, much greater than anything else in the network, then this approximately becomes Vi. Right? So what is the solution? Then in the total circuit, what is the solution? I remove this, put an R3. Okay. So as long as R3 is much greater than, I mean, so if you, in this case, is almost equal to Vi, if R3 is much greater than 1 over Gm. And no, not only 1 over Gm, 1 over Gm plus Rs. I mean, basically you get the idea, right? If it has to be, I mean, I think it's much greater than, yeah, it either has to be much greater than 1 over Gm or has to be much greater than 1 over Gm, much greater than Rs. But safe side is to do this. I mean, if you ensure Rs to be much greater than 1 over Gm plus Rs, then what? Good. Now the question that you are going to ask me is, I mean, if having capacitance to be really large value is a problem in area, isn't this a problem also because we want R3 to be much greater than? So in fact, it can also be, then that becomes a optimization part. It's not as if the area and the length of a resistor, area of a capacitor and the length of a resistor scales similarly. So then you have to then get dirty with the technology and see how much is the total area. Yes. So I want this to be exactly almost equal to here.
So then they should write R3 plus 1 by Gm should be much, much greater than Rs.
R3 plus 1 by Gm to be much, much greater than Rs, right? And that's right. What is the value? So numerator should be almost equal to R3. The denominator should also be almost equal to R3. Right? The R3 is the control variable. So if I satisfy that, then that gets automatically satisfied. Right? So that's the right. Any questions before we stop here? Yes. With the addition, okay, good question. So with addition of RC is the question point. So capacitor will act as a open circuit for question. So there won't be any current to RC. Right? Where will the current to RC go? Let's assume there is a current to RC. The current to RC cannot go to the capacitor, it cannot go that side. Again, right? Yeah. There was another question somewhere? No. Okay. Okay. Thank you.